All right, welcome back. Last week we started on loops, and hopefully you got a pretty good working hands-on experience with your reading this week. Let me turn it down just a little bit. But reminder that we are on Piazza, so if you have any questions, you can post there, or you can post to the YouTube chat channel here as well. But anyway, I wanted to start off with a little discussion on when to use for loops and when to use while loops. Remember that for loops use the keyword, surprise, surprise, for, and it locates all three of those elements on the same line. This is the initialization, where you start the loop. This is the continuation. As long as this is true, then you will execute the loop one more time, and it's always checked at the beginning of the loop. And then this is the iteration. In this case, we're only incrementing I by 1. So if I were 5, then it would go to 6, then it would go to 7, and that happens at the end of the loop. The major difference between a while loop and a for loop is that all three of those elements are in different lines, and you have a little bit more control on how and when those things happen. For example, the initialization still happens before the loop. The continuation condition right here, that also is checked at the beginning of the loop. Do we continue one more iteration or not? But this increment, that can happen anywhere within the loop body. If you don't, of course, then you have some problems, an infinite loop potentially. But you could do it at the top, you could do it at the bottom like I've done here. This will replicate the for loop from before where we count from 1 up to 10. And then we went through and enumerated all the differences between those. So why do we have two different types of loops? We actually have another third type of loop, a do-while loop that you probably saw in your reading that I'm not going to go over because it's not as useful as the others. The major difference is that the continuation condition is checked at the end of the loop. Therefore, a do-while loop is going to execute at least once, regardless of the continuation condition. If you want to read more about it, it's in the suggested textbook as well as I believe in Zybooks. But the fact of the matter is, you only need one loop control structure. We could get by in a language with only a while loop. We could get by in a language with only a for loop. Any one of those loops can be rewritten as an equivalent for loop or while loop or vice versa. But in general, we liked having multiple ways of doing things in a language because remember syntactic sugar? Sugar is not necessary, but it's really nice to have because it makes your language richer. It makes it easier to use. It makes it more intuitive. And here's one primary example, for loops and while loops. When do you use one or the other? When one feels more natural than another one. In general, you use a for loop when you know up front how many iterations you're actually going to go. If you want to count from 1 to 10, a for loop is very natural for that because you start at 1, you go up by 1, and you end at 10. If you 20 iterations, or if that's stored in a variable like n iterations, like you're going to experience in your lab tomorrow, then a for loop is way more natural than using a while loop. In general, you use a while loop when you don't know up front how many iterations you're going to go for. It depends on the input, right? You could be, on one input, you could be going for 5 iterations. On another input, you could be going for 50 iterations. You just don't know because it's part of the loop control structure. And one example that we're going to take a loop at is we're going to write a loop to compute how many digits are in a number, okay? Just to get some more practice here. Now, for this particular example, we've got a number here with 9 digits because I constructed it that way. But if I read that in from the user, would we know how many digits are in that number to begin with? No, that's what we're trying to compute. If we knew that up front before the loop, we don't have to write a loop because we have that answer, right? Just for this particular example, though, we know that that the answer should be 9. There should be 9 digits in this thing, okay? So I want to write a loop control structure here to compute that. I want to count the number of digits, num digits, right? And I'll start out with 0. And then what I'll do is I'll go along and there's 1 digit, there's 2 digits, there's 3 digits, etc., until I get to the end, and I will report how many digits there are, okay? So which loop is more natural? Do I know up front how many iterations I'm going to go through? Nope. So a for loop, does that sound natural? For I running from 1 up to n, I plus plus. I don't know n, right? So I'm going to go ahead and do this with a while loop, right? I'm going to count the number of digits, plus plus. Now, this loop is going to execute once for each one of these digits. There's the 1 digit, there's the 2 digits, there's the 3, 4, 5, 6, 7, 8, 9, and then at the end of it, I will report that it has that many digits. Printf, %d, that's going to be my original number, has %d digits. Right? And then we'll end the line. And we'll say n, and we'll also say num digits. Right? So now I need to come back and actually write this loop. Right? Some ideas. Throw out some ideas here. Yeah?
You could do it when it's not 0.
All right, so while this number is not 0, implicitly what am I doing then to the number to get to that termination condition when it becomes 0? All right, I'll divide by 10. What will that do to the number on the first iteration? It'll turn it into something like this, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, period 9, right? On the second iteration, it'll look something like this. On the third iteration, I'm moving the decimal point over, and I'm floating it, right? It floats back and forth. That's why we call these floating point numbers, because the decimal floats. It's kind of like scientific notation. But do I want it that fractional part? Does that get rid of the number of digits or decrease the number of digits? Nope. In fact, I won't make progress towards 0. I'll just have at the end, I'll have 0.123456789. That's not what I want. So I also want to incorporate integer division. If I divide by 10, this number is an integer, and if I divide by 10 another integer, what happens to it? Does it end up as 0.9? It ends up as this, right? Truncation, it gets thrown away. And now I've only got 8 digits. Do that again. Now I've got 7, 6, 5, 4, 3, 2, 1, and then it becomes 0 eventually. Right? Okay, great. So let's try that out. While n is greater than or equal to 0, what I'll do is I'll count the digit, and then I'll divide by 10. So n is equal to n divided by 10. So what about equals? This right here. Is this going to give me the answer I want? Well, let's find out. GCC, demo. And what should I always do? Always the wall flag to tell me if I'm doing anything wrong or suspicious. Right? A dot out. Ah, okay. What's going on there? I've got an infinite loop. How do I kill it again? Control C. Okay. So what was wrong? It got down to 0. 0 divided by 10. What is that? 0. 0 divided by 10. What is that? 0 divided by 10. What is that? Right? And now we're caught in an infinite loop. So what should it have been? Once it hits 0, that's when I want to stop, right? And get out of that. So let's go ahead and see if that makes a difference. And by the way, you notice that the wall flag, my linter, didn't tell me that I was going to get caught in an infinite loop. A linter can't do that, right? Not even with this simple code. All right, run it, and let's see if we get the correct answer. 0 has 9 digits. Well, 9 digits is the correct answer, but what did I do here? Yeah, I had the original number. I should have maybe made a copy of it. All right, so I'll go ahead and make a copy and modify the copy instead. Int, I don't know, value, right? And I'll copy over that value so that when I print n down here, n has been unaltered. And what I'll do is I'll make sure that I'm incrementing on the value now instead. And that was a lot of cut and pasting. How could I have saved myself some work by modifying line 17 here? Value is equal to the value divided by 10. Is there a shorthand way of doing that? Yeah. Divide equals 10. Right? Again, syntactic sugar. We like terser code. We like shorter code. We like abbreviations in English, right? We like acronyms in English, right? Well, we have the same thing in code. We have ways of shortening up our code to write it quicker, to read it quicker, and to understand it quicker. And that's one of them. Okay? Let's see if this fixed our woes. There, 1, 2, 3, 4, 5, 6, 7, 8, 9 has 9 digits. Works 100%. Well, let's try it with other things. 1, 2, 3, 4. Right? Always be testing, right? I'm satisfied that that works for that particular test case. What else should I try? Okay, maybe a single digit number. That should report 1, right? What else? Negative numbers? Negative 10. Okay. Let's find out what happens now. What's going to happen? 0 digits. Yeah, what's wrong?
It's because negative numbers are below 0.
Negative numbers are below 0 already. So does this loop execute? Nope. So how can I account for this? Yeah, go ahead. Oh, okay. If it's negative 10, then 10 if I flip it, right? So my value here will not just be a copy of n, it'll be a absolute value of n. Now, is that the correct absolute value or not? Okay, well, careful. Let's RTM or RTFM. Man, abs. Man is short for manual. Read the manual. Abs. There's abs, there's labs, there's LLabs, there's IMAX labs, etc., etc. What does it do? It takes an integer and it gives an integer. Well, I've got an integer, right? And I've got another integer, so I'm good on that. But what have many of you found out if you try to use abs in your labs, where you're using a floating point number? Is this the correct abs? Nope. Why? What's going to happen? If I take the absolute value of negative 10.5, what is it going to give me back? 10, right? Integer truncation. Because it truncates it to an integer, then it takes the absolute value and it gives it back. So you lose precision. What is the alternative if you have a floating point absolute value number? Fabs. Right? You could use fabs in this case, but why? Use the correct one. Now let's see if that corrected it. So GCC. There, negative 10 has 2 digits. I'm convinced it works there. Am I testing all possibilities, all edge cases? What's one last edge case that you might want to consider? Oh, letters? Hello. Can you do that though? Nope, that won't even compile. Right. I could put it into a string, and that will unfortunately compile, hopefully with a warning. Yep, warning. You cannot treat a string as a number. It'll run, it'll give me something nonsense though, right? That's not the number, that's the memory address. And that memory address conveniently has 10 digits. So we know how many digits that memory address has, but that's not what we want. What's another edge case here? It works for all the positive values that I've tested so far. It works for all the negative values I've tested so far. What happens in calculus when the function works over here, the function works over here, but it blows up at 0? I'll forget about 0. Can we, as coders, can we forget about 0 though? Nope. So let's try it. What's going to happen? 0 has 0 digits. Is that correct? No. So oftentimes what we have to do is we have to take care of those edge cases separately. None of this stuff applies, right? So if you want, you can go ahead and say, take that edge case and deal with it completely separate. If the value is 0, then we'll print out a special message. Printf 0 has 1 digit. Right? End the line and be done with it. And then I'll put all the rest of this stuff into one big else statement. There we go. There, 0 has 1 digit. If there are any other edge cases or corner cases, sometimes they're called, right? You have to look at the edge of things. Or in calculus, if this is the function's okay over here, the function's okay over here, but you divide by 0, what happens at 0? It blows up or it blows down or whatever, right? You need to handle that differently. That's an exceptional case, a corner case, or an edge case. Yeah, go ahead.
When you reach the max number for int or minimum number?
Okay, so let's find out what happens there. So what is the maximum number for an integer? 2.147 billion. 1, 2, 3, 1, 2, 3. So let's go ahead and kick it up a notch there. What would you expect it to be? How many was that? 6, 7, 8, 9, 10? Oh, okay. It compiles. Let's find out what happens. Right. 10 digits. Well, yeah, okay, I buy that this thing has 10 digits. But is that the thing that I wrote? No. What happened? Yeah, so if I've got a pint of beer right here, right? And I drink maybe a third of it, and I order another pint of beer, and I drink a third of it. I have 2/3 of a pint of beer, and I don't want to hold this anymore. I just want one cup. I pour my 2/3 over here into the first cup, into the or second cup into the first cup. What's going to happen to my beer? So once it gets to the top, there's too much more beer. I should stop pouring, right? But if I don't stop pouring, what happens to it? It overflows, and that's exactly what this is called. This is overflow. You only have a maximum number of bits to work with, 2.147 billion and change. When you start to add more to it, right? When I start and I add 1 more billion here, and I get 3 billion, it overflows, right? And what happens with overflow, it doesn't flow out and then drop to the ground. What it does is it's got this range. Here's the maximum value that you can represent. Here's the minimum value that you can represent, approximately negative 2.147 billion. So now take it, and it's a cup. And when you fill it up too much, instead of falling to the ground, it comes back around to the other side. Negative values, right? So what is the maximum value here? Let's see, 2 to the 31st minus 1. I can do this number, and that will give me a correct result. That's what I entered, and it has 10 digits. But if I go just one more, it's going to wrap around to the negative range that's representable here. That's called overflow. Yep, there we go. By the way, there is such a thing as underflow. It's just going too far negative and wrapping around back up to the top. And there's also underflow when for beer too, right? Have you seen those ones where they fill the beer from the bottom up, right, to avoid the foam, right? I guess you could have underflow somehow there where it pulls out your beer instead of filling up your cup. Yeah, go ahead. Question back there?
Yeah, so if you were to double that number that you got right there, would it go back to being positive?
If you go far enough, yeah. All right, that's going to give it to me. 6 billion should be enough. Oops. GCC, and then, yep, it went back to positive. So it's a cycle, right? You go too far, it comes back up. Go too far, and you're somewhere on the positive side or the negative side. It's just garbage values at that point, though. You can't tell anything because you've gone past the limits of what an integer can represent. All right. I'm going to go ahead and restore this here, 1, 2, 3, 4, 5, and then I'll put this in the notes so that you have it. All right. There we go. All right. Another item. Nested loops. Just as with if conditionals, you can have code within code blocks, within code blocks, within code blocks. You can do the same thing with loops, right? You can have a loop inside a loop, right? Loop. The inner loop, we call it. We refer to them as the outer loop and the inner loop, right? You can do this as many times as you want, but avoid 3 or more nested loops, right? Just because loops build on each other. For each iteration of the outer loop, you have an entire cycle of the inner loop. And what I mean by that is, let's go ahead and write a nested loop here. I'll just go ahead and go with n is equal to 10. For I running from 0, I is less than n, I plus plus. Oops. I meant n is equal to 10. There we go. Now that's my outer for loop. That's going to run from 0, 1, 2, 3. What's the last iteration that it's going to run for? I is equal to what? 9. Because I have strictly less than I, and I is 10. When I is 10, 10 is not strictly less than 10, and so it breaks out of that for loop. Now I can have an inner for loop here. Can I reuse I? Nope, I've already used I for the outer for loop. In fact, if I try this, it's going to tell me that I have a double declaration here. Oops, I plus plus. And all I'll do in my loop is printf. I'll print out %d, %d. This will be I and j. So I, j is equal to these two things. And the line I. And I don't have a j yet, so I'll just go ahead and go with I. But I'm going to show you that this won't even compile. Right? Oh, it will compile. All right. And what will happen? All right, fine, it'll work. That's the compiler saving me from myself. It's not a very good idea, though. So J, J, and J. Otherwise, you have two I's in scope and gross. All right. J, there we go. All right, so you saw a preview of what it looks like. When I compile this and run it, how many times is it going to run? That outer for loop is going to run for I being from 0 up to 9. In other words, 10 times. But each iteration, when I is 0, this inner for loop, that's going to execute 10 times as well, for j running from 0 up to 9. So it's going to be 0, 0 up to 9, 1, 0 up to 9, 2, 0 up to 9, etc. And you can see that it ran exactly like that. It ran from 0, 0, 0, 1, 0, 1, 2, 0, 3, all the way up to 0, 9. At that point, the inner for loop was done, and it jumped out to the outer for loop, starting incrementing to the next I, which is 1. And then it ran 10 more times. Then it ran 10 more times for 2. So how many times total did it run? 100. 10 times 10, right? You multiply those two things together to give you how many times it actually runs, right? Right? You can have nested for loops, but again, going 3 nests deep, that's probably not advisable. Right? Why? Well, it starts to compound. What if I did that? 100 becomes, how many times would it run if I had 3 nested for loops going from 0 to 10? 1,000, 10 times as long. Right? Now imagine if I wasn't running something small, 0 to 9, 10 times. Maybe I was running 100 or 1,000. Now it's 1,000 times 1,000 times 1,000. How many is that? That's 1 billion now, right? And that becomes noticeable. In fact, I'll show you. 1,000. 4. By the way, what where do I go to next? I, J, K. J or K is less than N. K plus plus. There we go. And print out I, J, and K. There we go. Oop. Say what? %D, thank you. How long is this going to take? Very long, but is it an infinite loop? No. It's not infinite. It'll eventually get done. But is there really any difference between an infinite loop and something that is going to take days, weeks, months, years, centuries? Right? No. Not effectively for humans. Right? We're not going to sit around and wait for this to happen. In fact, even if I didn't do anything, actually this might execute instantaneously, because the compiler might be smart enough to say, you're not doing anything, so I'm going to optimize that away. Nope, it didn't. All right, fine. Oh, there. It got done in a few seconds because it didn't have to do anything. So a computer is fast at doing a billion nothings, apparently, right? But it was still noticeable, right? It still took you a few seconds to do nothing. Haha. Right. Okay. So there's your nested for loops. Okay. What about some pitfalls? Just like with conditionals, we had some other pitfalls here. We had some pitfalls with conditionals. We also have some pitfalls with loops. So take a look at that code and tell me what's wrong. Do you see anything wrong? Yeah, that semicolon seems suspect, right? Which semicolon? That semicolon right there. I never wrote anything like that. What's going to happen here? Let's find out. You notice that I got rid of the wall flag because... Ooh. So what happens? It doesn't do anything. So I starts out at 0. while I is strictly less than 10, do what? Nothing. All right, go back up. Do nothing. Do nothing. Do nothing. All right? All right, let's kill that. How do I kill it again? Control C. Now let's go back and, like I've always said, use the wall flag. And it tells you this statement, but the latter is misleadingly indented as if it were guarded by the while. I think that there's something wrong here. This while clause does not guard, meaning that it doesn't do anything. Right? All right. So there's the problem with that one. It results in an infinite loop because of the misplaced colon. And again, yet another reminder to always use that wall flag as your linter. Right? Another pitfall. Consider the following piece of code. Look real hard. I got rid of the semicolon, so we're all good there. What's it going to do? Yeah. It never, because I forgot the increment, right? So it's an infinite loop. I forgot my plus plus somewhere, right? GCC, oh, come on. Come on, there we go. Now, the linter didn't help me in this case. The linter is not going to be able to detect infinite loops. Wow, it would be great if we had something like that, but there's a result in computability theory that says that the halting problem is undecidable. In other words, effectively, you can't write linters to detect every single possible potential infinite loop. Right? And it always prints 0. It does something. It's just printing 0 over and over and over and over again because I never make progress towards my terminating condition. What if I put the plus plus there? What's it going to print now? So I is 0. I is strictly less than 10. It comes in and immediately, before it prints, it increments it to 1. So it starts out at 1. Right? What's it end at? Let's find out. 10. Why? 10, so I++, it becomes 10 at some point. It prints 10 at some point. It comes back up here and it says I is less than or strictly less than 10. 10 is strictly less than 10? No, so it doesn't execute. And that's why it starts out at 1 up to 10. If I had less than or equal to, then what would it print up to? Yeah. 11. Kick it all the way up to 11. There we go. So be careful. Again, it goes to an infinite loop, and you have to make progress towards your termination condition. 2 more. One that you might encounter, and one that you might not. So again, look real hard here. What's missing? Brackets, curly brackets, right? So what's this going to do? The linter does help me in this case, right? Again, linters, static analysis tools like this, they find things that are that looks wrong. That's probably wrong. In other words, you indented here. It looks to me like you meant for this entire thing to be part of the while loop, but it's not because you forgot your brackets. Right? By forgetting the brackets, what does the while loop do? Let's go ahead and run it and find out. Prints 0 forever. And that's because the while loop binds without to the next code block. And if you put in curly brackets, that entire code block is the loop body. If you don't have those curly brackets, the loop body is limited only to the next executable line, which is the print statement. This is terrible practice. It doesn't matter if you have 1 line or 50 lines. Make sure that you're always writing the curly brackets, period. All right? All right, and then the last one. This is a real world one, by the way. Many of you may be too young to remember or never have had a Zune. But on December 31st, 2008, every Zune froze for 24 hours, for a 24-hour period. So let's ask DuckDuckGo, what is a Zune? It was Microsoft's answer. I'll just look at the images here. It was Microsoft's answer to the iPod, right, at the time. The video iPod had just come out, and it was $250 or something like that. The Zune was $50 cheaper, and it had an FM radio. and it worked with Windows. Like it was a non-Apple product. That was its other selling point, right? It didn't sell that well. It wasn't marketed that well, and it didn't have the backing, of course, of the iTunes store at the time. So not many Zunes were out there. I had one, of course, because I couldn't afford, or I didn't want to afford an iPod. But on December 31st, 2008, every Zune in the world, however many little there were, froze up for 24 hours. Why? Right? So let's take a look at the code here. This is code that was actually published, that was actually in the Zune subsystem. Right? It's very similar to what you did on your lab last week. It involved leap years. Well, was 2008 a leap year? Yes. December 31st, 2008 was the last day of the year. Therefore, it was day number what? There are 365 days usually in a year, right? But in a leap year, there's one more. So the number of days was 366, strictly greater than 365. So this while loop started executing. It had not executed at all for the last 2-3 years, however many the years the Zune was out, because nothing had been a leap year up to that point. Well, is leap year is true, right? 2008 was a true. So this if statement will execute. This else statement will not execute. So this if statement executes. Now, is days strictly greater than 366? No. So this will not execute, and we go down to the else statement, which is empty, right? Coming back all the way up to the top. Days is still 366, and so this executes again, and again, and again, infinitely until the next day, 367th day, at which point this is still true. It's still a leap year because the years have not rolled over yet. But now 367 is strictly greater than days, and everything corrects, and 24 hours later, just as mysterious, all the Zunes started working again, right? Because it jumped out of this loop after 24 hours of going through this loop, right? What's the fix? Yeah, greater than or equal to is what it should have been, right? What's the real fix, though? What did they not do that you did last week in your lab? Yeah. Oh, well, they could make an else statement, but what did you do in your lab that would have caught something like this? Testing, test cases. If you've got an extraordinary case like what happens on the last day of a leap year, what happens on the first day of a leap year, right? What happens to everything in between? Let's test for that. They never bothered testing for this. And now it was not a system critical. I mean, Zune owners couldn't listen to their music for 24 hours, right? So it was not that big of a deal. But imagine if you had a bug like this in, say, medical software that distributed insulin to patients, right? And bugs like that have happened where they give too much or too little insulin and people have died because of it, right? So these little things, right? The missing equals sign here can have huge dramatic impacts, right? And the only way that you know whether or not this is correct or not, or you have confidence that it's correct, is by thorough and rigorous unit testing. Right? That's going to be the focus for the next couple of weeks in your labs too. Right? All right, so there's the Zune bug. Questions so far? Saw a couple of questions. Go ahead.
Or not necessarily, but you can go back up so you can finish.
Oops. Yep.
Thank you.
All right. So it's common for the first or last iteration of a loop to be wrong, just like this one was. It's common to handle those exceptionally, like handle the last iteration separately, or handle the first iteration separately, or rewrite your loops to handle those and reorder your logic. Question way back there or not? No? Okay. All right. So we don't care what a Zune looks like. All right, let's get some exercise. So exercises. That's math. Let's do this one. This is finance. Right. So this will be fun. All right. Everybody knows how loans work, right? You borrow some money from the bank, and you have to pay interest back to the bank, and you have to pay monthly payments back to the bank. So the amount that you borrow is the principal, right? If I borrow, say, $10,000, right? And there are terms, like it's a car loan. So usually car loans are about 5 years. And there are 12 months in a year, so the number of terms is 60. 5 times 12 gives you 60 months. You're going to be paying this over the next 60 months. Your actual payment each month is determined by this equation right here. It's the rate, the monthly rate, times the principal, divided by 1 minus 1 plus the rate up to, raised up to the power negative n, where n is the number of periods, months of the loan, and usually. Okay? Don't worry about where this formula comes from. It's from finance. It's from somebody else figured that out. That's not our focus, right? We're going to use that formula in our program here, right? And what we're going to do is we're going to produce a loan amortization table, something that looks like this. So in the first month, we've borrowed $10,000. We have to pay a little bit of interest, and we have to pay a little bit back on that loan. The interest is calculated by taking the rate, say in this case it was 5%, not that great of a rate, but middle of the road rate here, 5%, and dividing it by 12, that gives you the monthly rate, because 5% is the annual interest rate. You divide that by 12, and you get the monthly interest rate. Whatever that happens to be, let's go ahead and go with 0.05 divided by 12, and that comes out to about that, right? Now I'm going to multiply that by my current balance. I borrowed $10,000, right? And that tells me how much interest I have to pay that month. There we go. $41.66.666666. Do we pay pennies and fractions of a cent on things? No. Instead, we need to round it to the nearest cent. We pay $41.67 in that first month in interest, right? Now, the monthly payment is, I forget what it is. I think it's $187 and whatever cents out of this thing. Whatever's left over in that monthly payment, that goes to principal. And that $10,000 that we owed is now only $9,852.96 because we're paying down the loan. The next month, we don't pay interest on the entire $10,000 because we don't owe $10,000. We only owe $9,852.96. So the interest goes down a little. The amount that we pay on the principal goes up a little, right? And so that's going to continue throughout the entire process until the last month in which we're paying only a little bit of interest and everything else is going to the principal to pay it down. And we've reached a new balance of $0 because we've paid the loan back, okay? Now this is the, I only put 6 in here, but this is like a 60-month loan, or 60, it's a 5-year loan. And so let's reproduce this table all the way down to the bottom, okay? Let me go ahead and get rid of demo here. All right, I'm starting completely from scratch. What's the first thing I do when I write a program? Careful, what should I do? The purpose, the author documentation, I heard documentation out there, the author header, right? So I'm the author. What else should I put in there? Date, 2021, it's September 13th. And what else do I need? The purpose. This program takes in loan data and produces, this is called an amortization table, a loan amortization table, right? How much you're paying each month to interest, how much you're paying to principal, etc. Okay. Next thing, what do? I need to bring in some libraries, right? I need to bring in the standard library, and I need to bring in, I'm probably going to be doing input and output, right? I'm going to bring in the standard IO library. I'm probably going to be doing some math, right? If I'm going to be raising something to the negative 60, I don't know how to do that, but the math library does. Okay. What's next? Main, okay. Int main, int argc charge star star argv. We'll get, you know what those are now, you just maybe not necessarily how to fully understand what the star star is. But let's go ahead and read in command line arguments. We're going to need three things. We're going to need the rate, the annual interest rate, the number of periods, month, or maybe we'll just read in years and we'll do the multiplication by 12 ourselves, and the actual principal. So let's read all those three things in as command line arguments. The principal will be a double. Simple. How do I read that as the first command line argument? Argv sub what is the first user provided command line argument? 1. Okay. Now, I'm going to need to convert that to a double. What do I use? A to F. All right. Principal, I don't know. What's next? Rate. Double annual rate. Rate equals A to F of argv sub 2. Okay. And then lastly, the number of years. Is that going to be a fraction? Have you ever heard of a loan that, well, I guess there are loans where you pay weekly if you want to, but like every month and a half you pay on the principal. That doesn't sound right. So let's go ahead and make it a integer, number of years. Right? Now is this A to F? Nope, it's what? A to Y, argv sub 3. There we go. Now let's do some basic error checking. We're expecting 3 command line arguments from the user, plus argv sub 0, which is the executable file name. So let's go ahead and expect 4 command line arguments. If argc is not equal to 4, then we will print an error message and quit on them because they didn't provide us enough data for us to actually work here. Printf usage, provide the principal, annual rate, and years as command line arguments. And the line, and how do I exit on them? Exit with a special error code that I'm just using as 1 here. Right? Now, let me go ahead and compile this and show you that by not providing any command line arguments, then it gives me this error messages and quits. Right? If I do provide command line arguments, what is it, $10,000 that I want to borrow at a rate of 5%, and number of years would be 5. Some months would be 5 times 12, 60. And it's happy about that, at least for now. It's not doing anything because I haven't written the rest of the program. Right? Okay. Next. I need to produce a table that looks something like this. So let me go ahead and write out the header here, printf, and the line. Right? So those are, each one of those is my column. The first month, month 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever. The balance for that month, the amount of interest that you pay in that month, and then the new balance. Right? Did I get all of them? Nope. There's the balance, the interest, the principal. That's how much I'm paying towards the principal, and then a new balance at the end. Okay? So I'm obviously going to need to write a loop to do this, right? I'm going to need to write a loop to go for each one of these months. So what kind of loop do you want to write? A while loop? A while loop is natural when you don't know up front how many iterations you're going to go for. Do I know how many iterations I'm going to go for? Yeah. Number of years times 12. Right? So maybe a for loop is a little bit better. Right? Now I could go int I starting at, where do I want to start? Maybe 1. I is less than or equal to the number of years. I plus plus. No? All right, suggestions on fixing that? This is only going to go 5 iterations instead of the 60 that I want. Right? So years times 12. What I could do is I could put that into another variable, months, if I wanted to. Or I could just go ahead and put it right here. Right? Now, is it a nice idea to say use I? Right? What's I actually representing now? If this is just a generic for loop, sure, I is good enough. But what is this actually representing? Month. So if it's representing the month, why don't you just call it that? That's one common thing that we saw in the hack 2. People would create a variable called, say, x, and then they'd put off in a comment, what was it, latitude. They put off a comment, x represents latitude. Why didn't you just call it latitude then? Then you wouldn't have needed to write that comment. Then it would have been more readable and understandable later on in your program. Like, what the hell is x again? I have to look up there to find out in your comment. Whereas if it were named latitude, degrees, latitude, radians, right? That's absolutely clear. So let's go with months here. We're going to want to print that out, of course, printf, %d, and the line, months, or month in this case. And let's see if this works so far, right? Iterative testing here. Looks like it worked in that it printed out all the months starting from 1 up to 60. All right, good. All right, what next? Put the cart before the horse here a little bit. What do I need to compute? I need to compute, one of the things I need to compute is the monthly payment, right, using this formula right here. In the formula, I called it P. Is that a good variable name? Double P is equal to this formula that I'm about to do. No. I mean, that's good for math. Mathematicians like single letter variable names, X, Y, A, B, C. And then when they run out of those, they go to Greek, right? And when they run out of those, they make them up, right? When they run out of those, then whatever, right? I shouldn't call it P. What should I call it? What does it represent? The monthly payment, right? So what was it again? It's this, rate times principal, and the rate has to be divided by 12 because it's a monthly rate. So, come on. Rate times principal, right? There we go. Divided by, and then from memory here, 1 plus or minus 1 plus, sorry, the rate has to be divided by 12 here. Do I have a worry of integer truncation in this case with the rate? No, but I don't have any variable called rate either, do I? What do I have it? Annual rate, so let's go ahead and fix that. So annual rate is 0.05 divided by 12. That gives me what I did with my calculator before, right? I have no problem with that. Yep, okay. Somebody posted some more information about the Zune on Piazza if you want to take a look at it. But anyway, we don't have a problem with integer truncation here because you're dividing a double by an integer, which remains a double, okay? What else was in there? 1 plus rate raised to the power n. So I don't know if this is because of the connection or because of my computer. OBS is acting okay. All right, so remind me, what was it again? Rate, so annual rate divided by 12, and then I raise all of that to the power negative n. How many powers? Math, libraries, POW function. I'm going to put a negative in front of a variable. Right? There's no problem with that. If it was negative before, it'll make it positive. If it's positive, it'll make it negative. And that's it. Save that. Let's print that out just to make sure that it's good. This would be dollar sign, because it's currency, percent F, and the line. Is there a way to improve this? Oh, 0.2, good. So let's go ahead and oops, my n, where's that? Oh, negative n, sorry. What does it get all in a parentheses here? Sorry. It is really lagging. Try that again. Okay, good. It works, but it doesn't compile. What am I forgetting? -lm Lincoln, the math library, so that it knows what the hell the POW function is. Let's run it and find out what the payment is. $188.71.2336. Is that a... Yeah, sorry, the stream is lagging, but it's only dropped less than 1% of the frame, so I think we're okay. But anyway, is that a dollar figure that you've ever heard of? No. So what should we do to that instead? it should be $188.71, period, right? We want to get rid of those fractions. How could I do that? That if I use %f in a print function, it's only going to round it for formatting purposes. It doesn't actually change the variable value. What if I round? Oh yeah, it would still be $188.71 and then a fraction of a cent, right? What if I rounded monthly payment? Round. What do you think that's not flavor too. The payment. Oh. All right. Let's see if that works. All right, monthly payment. Call it right. There we go. All right, and let's run it. I'm out of here just to see us improve the lag. Okay. Hopefully that gets a little bit better, but in any case, I am getting a new computer. I have no idea when. All right, there we go. Well, that's the old one. Here, I have to clear this up. Let's run one more time. Sorry. I'll go to the top. There. $189.00. Did that round it correctly? No. What was it before? $188.71 and then fractions of a cent? I don't want to round to the nearest whole number, 89 here. I want to round to the nearest tenth, or 100th, sorry, right? I want to round to the nearest cent. So how am I stuck? I could RTM and I could read the manual and find out, is there a round to cents function in the math library? Find out, no, there's not. What could I do instead? Now those are, will round up to the whole, the nearest whole number. If I leave it like that though, what's gonna happen? My monthly payment is now, what, $18,000?